This lecture introduces matrix algebra. For examples, we're going to talk about some algebraic rules for matrix operations. We'll discuss the idea of matrix identity matrix, the idea of non-singular matrices, and also the transpose of a matrix. Well, let's start with some remarks. For example, if you have two square matrices A and B, and then if you want to add A plus B, you get the same results as B plus A, okay? But then if you take A multiplied to B, most of the times it's not the same as B multiplied to A. That means matrix multiplication is not commutative, but matrix additions is commutative. Okay, well, here are some algebraic rules that is valid for any scalars alpha and beta, and for any matrices A, B, C, right, for which the indication operations are defined. So again, alpha and beta are scalars. A, B, and C are matrices. So first, if you take A plus B, you will have the same matrix and B plus A if the additions of the two matrices A and B are defined. And then if you take A plus B plus C, it will be the same as A plus B plus C. So you can group A and B, or you can group B and C and then add it to A later. Similarly, if you do not change the order of A, B, C, then A times B times C equals to A times B times C. Again, if you're not changing the order of the multiplications A, B, C, then you can multiply A, B first, then multiply to C, or you can take A and multiply to B, C. All right, distributions, if you have a matrix A multiplied to B plus C, you can distribute A into B and A into C. Okay. If you multiply two scalars, alpha, beta to A, then you can take beta multiplied to A and then multiply to alpha. If you have a scalar alpha and multiply by A times B, then you can multiply A alpha to A first and then multiply to B. Or you can move the alpha to multiply to B and then multiply to A. Okay. And if you have two constants or scalars, the sum of alpha and beta, and multiply to A, again, you can distribute alpha and beta into A. If you take a constant alpha multiplied to a sum of the two matrices A and B, you can again distribute alpha to A and alpha to B. Again, alpha and beta here are constants. That means you can move the constant around without changing the result. One more thing that you want to, another thing, not nothing, but this is again, I want to emphasize the matrix multiplication is not commutative. A times B is different than B times A. And then we can talk about the identity matrix. So our identity matrix is a square matrix. And it's called an identity matrix when you have all the diagonal entries are 1 and everywhere else is 0. For example, if I have an identity matrix, matrix A, let's say, and 3 by 3 matrix, okay, so you're going to have 3 columns and 3 rows here. So if A is an identity matrix if, well, A11 is 1, A1, 2, 2 is 1, and A3, 3 is 1. Okay, and everything else should be 0. Okay. So this a matrix A is identity matrix, and if usually we use I to denote an identity matrix, and because this is like a 3 by 3 matrix, so we'll say I 3 by 3. If we use I 3 by 3, usually it's denoted for an identical matrix of size 3 by 3. Okay. Well, so this is an identity matrix, and then let's call matrix A. And I want to call an arbitrary matrix. So I'm just gonna say A11, A12, A13, A21, A22, A23, A31, A32, A33. Now I want to show that if I take the matrix A and multiply to I, A multiplied to I, what do you got? So you will get row, columns, right? First row, first column. I will get this is 0, 0, so A11 stay. Okay. Second row, first column, second row, first column. So it's gonna be A12. Third row, first column, I would have A31. Okay. And then if I change the columns to the second column, I would have first row, second column, I would have A12, A2, and so on and so forth. So the result is if I take A times I will get A. Okay. And if I take I times A, I will get also A. If I times A, then I will take, let's see, first row, first column, right? So I get 1, everything is 0, so A11. Second row, first column, I would have A21. Third row, first column, I would have A31, and so on and so forth. So my product is going to be just equals to this is also just A. Okay, so now it's the same as A times I equals to I times A equals to A. If you take any matrix, you multiply to an identity matrix, you get that matrix back. Now we can discuss the matrix inversions that associates with the term non-singular or non-singularity or invertible. Okay, so if a square matrix is said to be a non-singular or invertible, if there exists a matrix B such that if you multiply A to B, it's the same as B times A and is equals to I, which is the identity matrix. Okay. then at that time, B is said to be the multiplicative inverse of A. All right. And if any square matrix A, if it has an inverse matrix, then that inverse will be unique. And sometimes you call an inverse matrix of A is A to the -1. It's an inverse matrix of A. Again, you have a unique inverse, and then you can denote the inverse matrix using A to the -1. And then now that you know what is a non-singular matrix, then a singular matrix is a square matrix that does not have a multiplicative inverse. So you cannot find a matrix such that if you multiply to that matrix, you get an identity matrix. So remember, non-singular, that means if A is non-singular, that means A is invertible. Okay, that means there exists an inverse matrix of A. And what is an inverse matrix? It's a matrix when you take A, multiply to that matrix. It'd be the same as that matrix multiplied to A, and it would have to be equals to I. So there's a theorem that associates with non-singular matrices and inverse matrices. So if A and B are non-singular n by n matrices, then A times B is also non-singular. If you multiply two non-singular matrices, you get a non-singular matrix. And the inverse of the product A times B to -1 equals to B inversed times A inversed. Again, since matrix multiplications is non-commutative, B inverse times A inverse is different than A inverse times B inverse. So keep in mind that if you want to find the inverse of A times B, you have to take the inverse of B times to the inverse of A. And this theorem here is called a socks-shoes property. Why does this called socks-shoe property? It's because, remember, if you want to put, so first you have to put in a sock, right? You want to wear your shoe, you have to put a sock. Put on a sock first and then put on your shoe. But then when you want to take out your socks, you have to take the shoes out first and then socks later. Okay. Again, keep in mind that only square matrices have multiplicative inverses or inverse matrices. You shouldn't think about the term singular or non-singular when referring to a non-square matrices. And then the next types, one of the special matrices is the transpose of a matrix. A transpose of any matrices. Let's say a matrix A has size n by n. So the transpose of A is a matrix B, right? Has a sign n by m, because its transposes mean you interchange the row by the columns. So let's say B, right? The matrix B has entries bji. So the entry bji of matrix B here, when B is a transpose of A, is the entry A little a ij. So you just see that the order of the row and columns interchange. Okay. Most of the times, people use A to the T as a transpose of A. A to the T is a transpose of A. So let's do an example. If you have the matrix A, then you want to find A transpose, okay? In order to find the A transpose, you just need to interchange row and column. So first, the first row of A will be the first column of A transpose. The second row of A will be the second columns of A transpose. And also the third row of A would be the third column of A transpose. All right. Now, next example, A transpose, again, I just take the first row and make it the first column. Second row, make it the second column. Third row, make it the third column. Okay. If I look at this A transpose here, it looks exactly the same as A. So I know that A transpose is the same as A. When a matrix has its transpose as itself, that matrix is said to be symmetric matrix. So a matrix, a square matrix A, is said to be symmetric if A transpose equals to A. It has to be square, right? Because if it's not square, then when you transpose it, the size will be different. So you can't have equal matrices when you have a different size. So it's symmetric. And you can see that it's symmetric when you see, pay attention to this matrix A here. So this is diagonal. Entries on the diagonals are different, it doesn't matter. But if you have entries that are reflected by the diagonal, they are the same, right? 3, 4, and 5. So that's why you know that A is a symmetric matrix. And you can clarify it by finding the A transpose. And if A transpose equals to A, then A is symmetric. Here are some algebraic rules for transposes. If you take a transpose of A and you transpose it again, you get back to A, right? You interchange the rows and columns, interchange the row and columns again, you get back to the original matrix, which makes sense. If you multiply a constant to a matrix A and you transpose it, you can take the constant alpha out and then you transpose 8 and then you multiply A transpose to alpha. If you have a sum of the two matrices and you transpose it, it's going to be just the same as A transpose plus B transpose. Okay. And again, if you multiply two matrices together, A times B, and you transpose it, you can separate it, but you have to take B transpose first and then multiply to A transpose. Again, is a form of Sachs-Schul's property. So Sachs-Schul's properties works for transpose matrices and inverse matrices. Okay, let's do an exercise. So let's consider this matrix R here, cosine theta, negative sine theta, cosine theta. In fact, this matrix here, you will see this matrix again in the sections, in the application sections. Learn about how to rotate some shapes using matrices, and you're going to use this matrix here. But for now, you're given this matrix here is non-singular. That means R inverse exists. You want to show that R inverse is the same as R transpose. Okay, so you say since R is non-singular, by the definitions R there exist R inverse, right? So R inverse means if you multiply R to R inverse, you get I, and vice versa. So on the side, I know that R times R inverse equals R inverse times R equals to I. Okay. So now you want to show that R inverse equals to R transpose. So let's find R transpose. So R transpose equals to, so you take the first row, it's become the first column. So cosine theta, negative sine theta. second row becomes the second column, sine theta over cosine, and this is cosine theta. So this is R transpose. In order to show that R transpose is the same as R inverse, and we know that R inverse is a matrix where you multiply to R and you get I, right? So let's try R times R transpose. See what R times R transpose, to see what it is, right? So R times R transpose would be cosine theta negative sine theta cosine theta multiply to R transpose, which is cosine theta sine theta negative sine theta and cosine theta. Okay, so what do we have here? We should take first row, first column, right? Cosine and sine. So cosine squared plus sine squared, which is 1. Okay. Next one, first row, second column. First row, second column. First row, second column would be here. So you take cosine times sine minus sine times cosine. So it would cancel out. Okay. And second row, first column, you will have sine, cosine, right? And cosine, negative sine, so it's cancel out. Second row, second column, you have sine times sine and cosine times cosine. So you would have cosine squared plus cosine squared, you have 1. So I just checked that when you take A times R transpose, you will get I. So this is an I, right? It's this identity matrix. Cool. The last one, that's only one statement, R times R transpose. So how about R transpose times R? Because as we know that matrix multiplications is not commutative. We might get different answer for R transpose times R. So R transpose would be cosine theta, negative sine theta, cosine theta, times cosine theta, minus sine theta, times cosine theta. Okay. See what we have here. So first row, first column. First row, first column. You have cosine, you have sine, right? Which is cosine squared plus sine squared is 1. Good news. Now you have first row, second column. Sine times cosine times negative sine plus sine times cosine, so it's cancelled out, and so on and so forth. So if I keep doing this, I will get take the second row, first column, you will have negative sine cosine times sine, so it will cancel out. And then the last one is second row, second column, you will have sine, negative sine is sine squared, plus cosine times cosine is sine squared, plus cosine squared is 1. All right, we just show that if we take R transpose, R times R transpose, we get I, and we take R transpose times R, we also get I. That's what we just show. So from this statements here, we can conclude that R transpose is acting just like the inverse of R, because R times R inverse equals R inverse times R equals I. Okay. So again, we just show that R inverse is the same as R transpose for this matrix R.